talking about exponential and logarithmic models, but I'm only going to cover two types of models in this video, specifically exponential growth and decay models. So like I was saying, we have different types of models. We have exponential growth, exponential decay, and we have these other three types of models when we talk about logarithms or exponential equations. However, in this video, I'm not discussing 3, 4, or 5. I'm only focusing on 1 and 2. So let's take a look at this first example here, modeling the growth of U.S. population. The graph in figure 3.19 shows the U.S. population in millions for 5 selected years from 1970 through 2003. In 1970, the U.S. population was 203.3 million. By 2003, it had grown to 294 million. Part A wants us to find the exponential function that models the data for 1970 through 2003, and then it's asking us by which year will the U.S. population reach 315 million. All right, before we start addressing this, a moment ago I pointed out that our models are typically y equals the following. However, I particularly like this model, a equals a. 0 represents the beginning or the start, whatever the population is that I'm beginning with, the bacteria size or the original percent, whatever it is that I'm looking at, that's what a sub 0 is going to represent. E to the power of kt. Okay, so a again is going to be your final amount, quantity, or population size at whatever time that we're looking at. Again, a sub 0 is going to be whatever it is that you're starting with. K is going to represent the growth rate, however we're depreciating. So let's call it rate. And T is going to represent time. Sometimes it specifies years, months, whatever it is that the problem is looking at. So based on that, now I can start identifying things from this word problem. This word problem, my initial population size in 1970 was 203.3 million. So that's what I started with, 203.3. And then I finished in 2003 with 294 million. We also have the time. I just need to figure out how many years are there between 1970 and 2003. 33 years. So now the only thing we're missing from the model is k. So we need to solve k, and that helps us find the exponential growth model. Okay, so now all I have to do is direct substitution. So let's go ahead and do that. So we have 294 equals 203.3 e to the power k times 33. And now I have an exponential equation that I can solve for k, and that's exactly what I'm going to do. Alright, so in order to solve for k, I want to start by dividing both sides by 203.3. And then I'm going to end up with e to the power of k times 33 equals 294 divided by 203.3. What's the inverse of e? Okay, so I'm going to introduce ln on both sides. Remember, this is grouped. These are inverses. So now I'm left with 33k equals ln 294 over 203.3. I'm going to divide both sides by 33. And then I'm going to approximate k to 3 place values. So go ahead and put this into your calculator. Alright, so rounded to 3 place values, we get 0.011. And now we have our model. Remember, a is going to be our final quantity. We started out with 203.3 million. E to the power of 0.011, and I'm going to express t in here to represent whatever time frame. This is now my model for the given equation. But remember, it was 2 parts. So let's take a look at that second part of the question. All right, so we looked at our exponential model, and that is part A. But now it's asking us, by which year will the U.S. population reach 315 million? So let's duplicate our model here so we can answer this question. So remember, it was A equals 203.3 e to the power of 0.011 t years. I'm looking for which year, so we need time, t time. Will the population reach 315 million? Well, remember, that represents A. This is your final quantity after t years or months or whatever it tells us the time is. So I'm going to go ahead and I'm going to substitute that in for A. And now I'm going to solve it like I did before. So I'm going to divide by 203.3. And we're going to get e to the power of 0.011 t equals 315 divided by 203.3. What's the inverse of e? ln. Remember, this is grouped. And now I have 0.011 t equals this. So in order to get t by itself, divide by 0.011. So t equals ln 315 divided by 203.3 divided by 0.011. Remember, we're talking about years, so let's approximate to the nearest year. Go ahead, put it in your calculator and check your answer against mine. Okay, so we got 40 for t. However, our question says by which year. So what do I need to do with that 40 in context of this problem? I need to add it to the original year, and we started at 1970. So 1970 plus 40 is 2010. So our answer for part B is 2010. So this was kind of like a 2-part problem. I needed to find t and then add it back. That's not always the case in the problems. Let's take a look at a different type of an example so you can see that that's not always the case. Alright, so here's another type of example. So we have the number y of hits a new website receives each month can be modeled by. So here they're nice. They give us model, somewhere to start with, where t represents the number of months the website has been operating. So here the t is in terms of months. In our previous example, t was years. So make sure you're paying attention to that in context. In the website's 3rd month, there were 10,000 hits. Find the value of k. So now we need to figure out the rate of increase. Okay, and then we're going to use that model to predict the website's number of hits after 24 months. So first, let's start answering the first part. Let's find k. 10,000 represents our final amount after 3 months. So let's start substituting. This is a, or y, and this is t. Okay, so let's go ahead and substitute. 10,000 equals 4,080 e to the power of 3k, because we're missing k. Now I'm going to do what I did in my previous problem. A little less work here because they gave us the model, so they were nice. And now we're going to end up with e to the power of 3k equals 10,000 divided by 4,080. Introduce the inverse of e, which is ln. And then I'm going to be dividing by what, guys? 3k is approximately whatever I get here divided by 3, right? So k is approximately whatever I'm getting here, or equal to, if I'm leaving it in exact terms, ln 10,000 divided by 4,080 all over 3. Approximate it to, let's see, 3 place values. Alright, rounding to 3 place values, we end up with 0.299. Okay, so now we have our model. Our model is A equals, I like A, you can put Y, whatever you want, 4,080 e to the power of 0.299 t. Now I can use that model to do what the second part of the problem is telling me. predict the number of hits the website will receive after 24 months. 24 represents T, so all I have to do now is substitute 24 in for T. So here, put 24. A equals, and notice that this is going to be straight calculator input. So put that into your calculator, check your answer against mine. Notice that it's the number of hits, so round up to the nearest hit. A equals, or is approximately. Alright, so how many hits are going to happen after 24 months? We're predicting that 5,335,282 hits for that website. Alright, let's take a look at something called carbon dating, the Dead Sea Scrolls. Use the fact that after 5,715 years, a given amount of carbon-14 will have decayed to half the original amount to find the exponential decay model for carbon-14. That's part A. Let's just focus in on that right for this particular moment. I'm not even going to read portion B. Let's focus finding our decay model. Remember, I'm still going to use the concept of A equal, your final amount is equal to your original amount, e to the power of kt. Because this is a decay, I expect k to be negative. If it was an increasing or growth, I expect k to be positive. Okay, so I expect it to be negative k, whatever it is the solution comes out to be. So now I need to just start substituting some concepts here. The only thing I'm given is this, and this is enough. I have after 5,715 years, that's t, and then it tells me half the original amount. My original amount is a sub 0. So let's go ahead and start substituting that. I know my original amount is whatever this is. E to the power of, I don't know k, we're going to solve for that in just a moment, 5,715. Well, if I begin here, and the half-life happens after this many years, I must equal half of whatever it is that I'm starting with. And now if I divide both sides by a sub 0, I end up with this. And I can solve for k. Just like I did before. What's the inverse of E? ln. So let's introduce ln to both sides. And we're left with 5,715k equals ln of a half. What do I do to both sides now? Divide by 5,715. Put that into your calculator and tell me what k is approximately. Alright, so you should get approximately, I noticed that I added more place values here because if I just do 3, we can't do anything with 0.000. So I rounded to 6 place values. My model now is A equals our original times E to the power of negative 0.000121 t. And now I'm going to use that model to answer portion B. So let's take a look at portion B. Okay, so let's take a look at part B. In 1947, earthenware jars containing what are known as Dead Sea Scrolls were found by Arab Bedouin herdsmen. Analysis indicated that the scroll wrappings contained 76% of their original carbon-14. Estimate the age of the Dead Sea Scrolls. So we already have a model that we can use to predict. Okay, this is telling us this is enough information, 76% of the original. Remember, this is the original amount. Think about substituting it with 100%, okay? And we're going to end up with 76%. And I'm going to use decimals. So what I'm saying is, this is what we start off with. And then I end up with 76, no, not 75. Okay. I end up with 76 of my original amount. And if I divide both sides by A, then I get 76% is equal to E to this power and I can solve for t. So I'm going to go ahead and introduce the inverse of e, which is ln. And now I end up with my exponent equals ln 76%. Make sure you put in decimal form. Now if I divide by this, I can determine the time. So put that into your calculator and round up. We're talking about time, so you want to round that up. T is approximately, okay, so you should end up with 2,268. What this means is that the Dead Sea Scrolls are approximately 2,268 years old, plus the number of years between 1947 and the current year. Okay? But this is enough for me. We can keep it at this. Let's take a look at another example. Alright, so example 3, the half-life of radium-226 is 1,600 years. What is the annual decay rate? So we're looking for K. And how long will it take for 30% of the radium to remain? So again, we want to start by finding that model. And I like using this model. Remember, A in here represents what our original at whatever time we're starting at, 0. And then our final amount, power of KT, we're looking for K to begin with, and then we're looking for T for question part 2. So let's start substituting. I know that it's telling me I'm going to end up with half. Okay, I won't completely erase it until we talk about it. Half of my original, e to the power of K times T, our year in this case is 1,600. Now I divide both sides by A. I end up with half is equal to e to the power of K times 1,600. Introduce ln on both sides. I get 1,600, K equals ln half. Divide by 1,600 on both sides. K is approximately, and let's round to a few place values here. So that's what we end up for K, and now we can say that our model, that's our annual decay rate. Okay, that's K, that's what we were looking for, and let's call that part A. Part B, how long will it take for 30% of the radium to remain? So I'm kind of going to shortcut because I've already been talking about it. We could say that we're going to end up with 30% of our original, and remember I divide my original out, e to the power of negative 0.12343 times t. T is what we're looking for. So now I'm going to start by introducing ln to both sides. This reduces, we're left with negative 0.1230433 t equals ln 0.30. Divide by all of this. Put that into your calculator and let's estimate the time. Alright, so you should end up with 2,781. So in context, remember we were looking for how long will it take for 30% of the radium to remain? Approximately 2,781, and it's in years, so I want to make sure I specify that.